Hi. This is going to be the first of a series of units on graphical model inference. Remember, we needed to do graphical model inference in order to compute the back propagation from an exponential softmax back to the tensors that define the graphical model, which are then computed from a deep network. So the first approach to doing this graphical model inference is Monte Carlo Markov chain sampling. This is not an approach that's highly recommended. It's quite slow. However, the mathematics behind this approach are generally useful. For example, we used a very similar mathematics in analyzing the learning rate as temperature in SGD. We talked about stationary distributions. So this is going to be all about the stationary distributions of stochastic processes and making those stationary distributions equal to the model probability distribution so that we can sample from it. But let's review sort of where we were. So here's what I just said. We've shown that if we have a deep graphical model that's defining these node potentials and edge potentials with a deep network, we can back propagate through that final softmax if we can compute these marginal probability distributions under the model defined by, under the probability distribution defined by the model on node value pairs, these marginal distributions, and also on edge pairs of values. So if we can, the idea here is if we can sample from this distribution, then we can compute these marginals by sampling. So what we're going to do is we're going to define a stochastic process whose stationary distribution is the model's probability distribution. And then we're going to run that stochastic process long enough that we hope we get to the stationary distribution and then see where we land. And that's a sample from the model probability distribution. So we're going to look at two particular stochastic processes, Metropolis and Gibbs. There are more exotic ones. There's a Hamiltonian MCMC that puts in a notion of momentum. Again, sort of reinforcing the connection between SGD and MCMC. So let's first look at Metropolis. So in Metropolis, we're going to think of these global assignments, an assignment of a local value to every node, as states of the process. The states of the process are the global assignments. And we're going to define a neighborhood relation on these states where two states are neighbors of each other if they only differ in one node. So the Hamming distance between them is 1. And the process is only going to make transitions between neighboring states. And the number of neighboring states now is reasonably small, right? It's the number of nodes times the number of possible values of those nodes. So this process is going to be feasible to implement. It's not, and it's going to have two requirements. So we can define it abstractly. We're going to define it abstractly on a set of states such that we have this neighborhood relation on states. And we're going to require that the number of neighbors of every state is the same. And we're also going to require that the neighbor relation is symmetric. If one state's a neighbor of another, then the reverse is also true. If A is a neighbor of B, then B is a neighbor of A. So we can just take any state space under these abstract conditions and define this Metropolis process. Now, the other thing about the process is it has to be defined on the scores without knowing the partition function, Z, because that's the thing that's hard to compute, is the partition function. So the Metropolis process can be defined on the scores. We're going to initialize the process to be some state, some global assignment. And then we're going to pick a neighbor uniformly at random. And then we're going to decide stochastically whether or not to move to that neighbor. So it's a stochastic transition. It's stochastic in that we pick a random neighbor and we decide whether or not to go there. So if the neighbor that we picked has a better score than our current state, in some sense it's a more desirable, that implies that it has a higher probability under the softmax distribution. If it has a better score, then we make the transition with probability 1. We take the next state to be the random neighbor. If the score is worse, or at least no better, then we may or may not take the transition with probability e to the minus delta score, where delta score is defined in a way that makes it positive. So with this probability, we take the transition, and otherwise we just stay where we are. So we always go to a better state. If it's a worse state, we may or may not take the transition probabilistically with this probability. That is the Metropolis process. Now, what we want to show is that the softmax distribution that the model defines is the stationary distribution of this process. So what we want to show is if we draw from the distribution we want, the softmax distribution, and take a transition, that the probability distribution over the next state is still the softmax distribution. It's still the model's probability distribution. So to prove that, first I'll just introduce notation. I'm going to let Q of a state be the probability that we get to that state if we first draw from the model's distribution and then take a transition. So Q is sort of the next probability distribution when drawing from the model distribution. And what we have to show is that Q is equal to the distribution hasn't changed. That Q is equal to the model distribution. This is what we have to show. So Q of a state, intuitively, this is Q is after we do a transition, is equal to its state before its probability before the transition, plus a flow in minus a flow out. So I'm thinking of these probabilities as like an amount of mass. It's an amount of probability mass. And I want to know how much probability mass do I have in this state after the transition? Well, it's equal to the amount of mass I had before the transition, plus the amount of mass that flowed in from neighboring states, minus the amount of mass that flowed out to neighboring states. So the next probability is the previous probability plus the flow in. And the flow in is just the sum over all the neighboring states of the flow in from that neighboring state, which is the probability of that neighboring state times the probability that if I pick that neighboring state, I take the transition from that neighbor to this state. So this is the flow in. It's the probability mass assigned to the neighbor state times the probability that I take the transition from the neighbor state to this state. And similarly, there's a flow out. The flow out is the sum over neighbor states of the probability of the state I'm in times the probability of moving out to that neighbor state. Okay, and I want to show, what I'm going to show is that the flow in equals the flow out, and hence we're at a stationary distribution. So detailed balance. So to show that the flow in equals the flow out, it suffices to show that for every edge, for every neighboring pair, the flow across that edge in each direction is the same, right? So I want to show that if y and y prime are neighbors, then the flow from y prime to y equals the flow from y to y prime. The flow across that edge is the same in both directions. And so the flow from y prime to y is just the amount of mass in y prime times the probability that I take a transition from y prime to y, and similarly in the other direction. Okay, so without loss of generality, I'm considering an arbitrary edge, and I'm going to prove this detailed balance for the Metropolis process. So without loss of generality, I'm going to assume that y prime is the state with a higher score. So Metropolis is defined by this transition probability that says if I'm in y prime, the probability of going to y is the probability of picking y as the neighbor, which is 1 over n, times the probability of making the transition. And if we were assuming that y prime is the better score, then this may or may not make the transition, even if it picks y as the neighbor. And the probability that it makes the transition is e to the minus delta score. Well, e to the minus delta score is equal to, even though I don't know the partition function, it's equal to the ratio of the probabilities, because the partition function cancels in this ratio of probabilities, and the ratio of probabilities is just the ratio of e to one score to e to the other score, which is e to the minus delta score. The probability of the transition in the other direction is just 1 over n. It's just the probability, because this is better scoring. If I pick this as the neighbor of that to consider the transition, it'll go with probability 1. So, so this transition is just 1 over n. So what I get is that this transition probability is equal to the ratio of the probabilities times that transition probability. And that is exactly what I need for the detailed balance. Okay, so what I've done is I've shown that the model distribution, the softmax distribution, is the stationary distribution of the Metropolis process. Okay, now Gibbs sampling. The idea, the intuition is that the Metropolis algorithm wastes time by rejecting samples. When it picks a neighbor with a lower score, it may or may not go there. And if it doesn't go there, then it's sort of wasted a step. Gibbs sampling avoids this kind of move rejection. In Gibbs sampling, we select a node at random. So now it's going to be important that we're looking at this global assignment. So we've got a graph, we've got a set of nodes, we're going to pick a node at random, and we're just going to update the label at that node. And the way we're going to update the label at that node is to look at the conditional probability of the distribution of values at that node, given all the current assignments to the other nodes. And the idea is that that's going to be computable from the score. We're not going to have to know Z. So just in terms of notation, if I'm at a global labeling Y, I'm going to let Y minus N be the labels of everybody else other than N, other than node N. And if I've got a set of neighbors for N, this is like I'm going to assume that this is a Markov blanket, that because all of the scores in our model are either node scores or edge scores, if I take all the neighbors in the graph and look at those edge scores, that's determining all of the values that influence the distribution on this node, all of the values, other values in the graph that influence this distribution. It's the Markov blanket. So this is going to be, I'm going to use this notation for the restriction of this assignment to the neighbors of N. So the Markov blanket property, I just sort of said it at a very high intuitive level, is that the probability distribution for this node given the other nodes, so this is the probability distribution over what we're going to assign to this node given the other nodes, is equal to the probability distribution of this given its neighbors. And that's sort of intuitively clear because the neighbors are the only thing that influence the effect of picking this node by virtue of the edge potentials. So in Gibbs sampling, what we're going to do is we're repeatedly selecting a node at random, and then we're going to draw Y from this probability distribution of this over this node given everybody else, which is equal to the probability of this distribution of this given the neighbors. And this can be computed without knowledge of Z, because I can simply compute a score for this and for each value of this, which includes its unary potential and all the edge potentials just to the neighbors. And that score that involves just the edge potentials to the neighbors is sufficient if I take the softmax over that score that's just looking at the Markov blanket. That's equivalent to getting this marginal distribution. And then I can compute a normalizing constant for that softmax, because that's a small softmax. And then I can draw Y, the next value of this node, from that. And so you can show that this, it's easy to show that this process has the right stationary distribution. This process is if you start from, if you draw from the model distribution and do this update, it's still the model distribution. So that's what we're going to do with MCMC sampling. Thanks.